Today I would like to talk about reinforcement learning. As I have observed in many surveys that most of the practitioners of data science use supervised learning in their applications. Some of them use unsupervised learning, but people who are using reinforcement learning are still in minority. Even though when you go look at the media reports and come across these kind of headlines, AlphaZero mastered scheme or AlphaGo defeated a world champion, AI achieving superhuman performance, or the news something like this. The interesting part is most of these things are done using reinforcement learning. So today I thought to talk a little bit basics about what reinforcement learning actually is and how can we use it. So let's discuss some of the important terminologies in reinforcement learning. So the first and the most important part in reinforcement learning is something called agent. Agent is the entity which performs all different kind of actions. And second part is the environment. So an agent interacts with the environment in few different ways. First, agent takes an action, and in return environment provides some rewards to the agent. Other thing which environment provide to the agent is the observation what's around the agents. So we can divide these terminology into two parts: reinforcement learning entities, agent and environment, and communication channels, action, reward and observations. So rewards, we can say rewards are such in a game. Rewards can be a score as a positive reward and penalty as a negative reward. If your agent is trained in a financial as a stockbroker, then your positive reward is your profit and negative reward is your loss when you buy or sell a stock. Suppose you want to train your pet. In this case, if your pet obeys your order, what you want it to do, then you give it a treat. That's a positive reward. And if it doesn't follow your order, then you don't give it a treat, a negative reward, and pet learns accordingly. For a student, passing grade might be a positive reward and a failing grade might be a negative reward. And in the case of a bot who wants to go through an obstacle course, if you want to train a bot, then maybe the bot doesn't collide with anything, like a minimum collision is a positive thing, or colliding might be a negative reward, or the bot has to go much faster to cover the obstacle course, then speed might also be a reward. Now agent in this case will be player in the game, or the trading system broker in the financial market. Pet is the agent, and student is the agent, or a bot in the agent in the cases I discussed before. On the other hand, environment is everything around the agent. You can say it's the whole universe, but we don't go that far. And agent communicate with the environment using three communication channels as I discussed before: rewards, actions and observations. This brings us to action. So action, what we defined is what agent does. Like player, if you are playing a game of Pong, or any other game, going up or down, or in another game, go forward, go backward, is the action player takes. Trader buys and sells the stocks. Pet sit and fetch. It's action once you give him a command. So, and there are two types of action typically described: discrete and continuous. So suppose in the example where I say player going forward and backward, it's kind of a discrete actions. On the other hand, if you think about a self-driving car, if the car has to move its steering, turn its steering, then it doesn't have to be like full 180 or minus 180 degrees. It can be anywhere. Similar to if it has to apply a brake, this can't be soft or a hard brake. It can be anywhere in between. So action we can say are discrete and continuous. In the final is the observation. This is the second information channel from the environment, and if you think about it, what was the first? It was the reward. So in observation is all information from the environment to tell the agent what's about its surroundings. So for example, in games, the current position in state in the game or the observation which might decide the action to take, which might decide the agent to take certain actions. Environment can be game plus your opponent skills, your opponent mood, anything can be environment apart from that. Same in the trading, stock and bond prices, market news can be observation, while environment can be the whole financial market, weather, global condition and whatnot. So after deciding all these 5 important terminologies in reinforcement learning, let's put it in a small quiz. So this is a self-driving car and it's approaching a red light. So what do you think will be the agent? Well, agent will be the self-driving car because it is the one who is taking an action. Environment will be everything around it. Observation will be what the state of the light. There are pedestrians around. There is a crosswalk. Reward will be if when we are training the car and if it jumps the red light, then it's a negative reward. While it stops at the red light, it will be a positive reward. This brings us to the second part in discussion of the terminologies in reinforcement learning, Markov decision process. We will approach Markov decision process in few steps. First we discuss what Markov chain, then we go to Markov reward process, and finally Markov decision process. So Markov process or Markov chain, you can say you have a system where you can only observe, so you are not taking any action. And what you observe are called states, and the system can switch between these states. So by definition, it will be a set of states that the system can be, and you have a transition matrix with transition probabilities that defines the system dynamics. So let's put it in a real life example so that will give you a much more better feeling what I'm talking about here. So suppose I decided to lose weight and I have very simple states to observe. I sleep, I drink coffee, I exercise and I eat food. And all these 4 states, I transition from one state to other as described from these arrows, like I go from sleep to coffee, then go to exercise, then eat food and come back. So this is your system dynamics. Now I am observing my system for a while, and what I have observed that I go from one place to another for a certain number of times, which can we say that is like a probability. So when I wake up, chances are like 70% of the time I will go and drink coffee, but 20% the chance that I go back to sleep. From coffee, 60% chance I go for exercise, but I might decide to skip the exercise and directly go and eat food. There are 30% chance for that. So what we can say is that we can define a transition matrix where we are defining the system dynamics based on probabilities. So this is one of the important terms we should remember because it will come in play in the further discussion, is the transition matrix. Other term is the episodes, which you might be quite familiar with. It's just like from one state we are moving to another state and we are keeping track of it. So we are going from sleep to coffee to exercise to food and sleep, or sleep, coffee, food, sleep, no exercise looks like in this case, and we observe them long enough and we will be able to get the probability in the transition matrix which I shown before. This brings us to Markov reward process. So as I discussed rewards before, we can quantify the rewards. We can say it can be any scalar number, plus, minus, and there's another quantity called gamma, which goes from 0 to 1 and it's called discount factor. So for every episode, suppose we want to know what is the total rewards by the end of the episode, what can we do is we can add up all the rewards we are getting from one transition to another, and we are going to use a gamma factor. And what gamma factors allows us to do is to decide whether how much our states are possible from where we are. So it gives a certain kind of takes care of certain kind of uncertainty from the states which are far away from our current states. However, if you put gamma equal to 0, is absolute short-sightedness that we only know the next state. On the other hand, if gamma is equal to 1, is a perfect visibility for all the subsequent events happening. So let's go back to our same slide before. So we have a transition matrix and our states, but in this case we are going to put some more rewards also there. So suppose if I sleeping and wake up and go back to sleep is not a good thing, so I get a -1 reward. On the other hand, if I go drink coffee and go to exercise, a +5 reward. And if I exercise and I stop and go back to doing exercise, a 10 reward. So we can put it in another matrix. We call it a reward matrix. Based on that, let's calculate the rewards. This is the same equation we discussed before. Now in this episode, what will be the total rewards? So, and we are assuming gamma equal to 1, so there is no discount factor here. So for sleep, to coffee we have +1, coffee to exercise we have 5, for exercise to food we have 1, and from food to sleep we have 0. So total rewards are 7. On the other hand, in this episode, for the same state of sleep, we have a different reward of -5, because we see we have skipped exercise here. So this is a slight problem here. So now for each states, our total rewards are depending on the episode we are going through. But if you want to get the average value of the state, then we have to introduce another term called value of a state, and this is one of the most important terms we use in reinforcement, particular algorithm of reinforcement learning. What value state basically is average large number of episodes and get a mathematical expectation of returns, which you can define by this equation. So for any state, that's the expected value of the state. So in this case, for the sleep, we take the probabilities from the transition matrix and the rewards from the reward matrix and multiply and add them together. Here I am assuming that gamma equal to 0, like a absolute short-sightedness. Now in the case of exercise, you will see the value of state is now 1.9. So as we can say that to be in the state of exercise, the most valuable state to be in to lose weight. But what's happened when gamma equal to 1 in this case? If you have observed, all the states are in this cycle, there was no end state. So what will happen is that we keep on adding the rewards and our value of state will become infinite. So the discount factor we discussed before is also comes into play in there, because its value is typically 0.9 to 0.99. then you will be able to get an approximate value of state, and it won't be infinite. That brings us to the Markov decision process. Here, before we are also choosing the actions. Previously, we were just observing, and the rewards depends on what action we take. So suppose we have a robo car which has really bad accelerator, brakes, and steering wheels. So now, if I want to go forward, there are only 80% chance that I will go forward, and 20% chance I will stay where I am. Same if I want to go to left or go to right. So now you see your transition probability also depends on your actions. So instead of a two-dimensional matrix of transition probability or transition matrix, we have a three-dimension now, which the third dimension is your actions. So if you go forward, it will remain in the same state, 20% of chance, and 80% of chance you will move forward. So this is your Markov decision process from point of view for reinforcement learning. This brings us to the second part of value, which is value of action. So now I have the same car. Here 50% of chance it go forward and it will get a reward of 40. For 25% of chance it will go left or go right. Same thing if I want to go to the left, you have a different transition probabilities and rewards are a little different here. Same for the right or going backward. So now if I want to calculate the value of a state, we have to take care of we have to think about what action we are taking, and that's come into play from the Q value. So let's say this F is for forward, L for left, R for right, and B for back. The Q value, if you are in state S0 here and you want to go more forward, is your probabilities to go more forward multiply with the reward 40, and same thing going left probability and getting the reward of 5, moving right, getting the probability with the probability of 25% and getting reward of 10. And if you see there, I have not defined any other state after that, so it's easier to calculate the Q value for explanation. The same way we can calculate the Q value for going left or going right or going back. Now if we have to find the value of a state, we find the action which gives us most highest rewards or highest Q values. So that will be the Q value for moving forward, and that's the final value of a state, which is 23.75 in this case. In terms of mathematics, you can define this with the following equation. Q, if you are in certain state S and want to take an action A, is the summation of probabilities and the next state from there. This equation, if you see here, came from Wellman equation. Now your value of a state will be, as we discussed before, maximum value of Q for we can have if we take action, particular action. So we select an action which gives us the maximum value of Q. These two equations can be combined and rearranged to come up with this following equation. If you can see here, if you put S prime here, S A prime and A prime, you can move these values over here. And this is the equation which is typically used in the first order algorithm, which you might use when you are trying to learn reinforcement learning, that is Q learning. And this brings us to the final terminology as of now to learn reinforcement learning. There are many other terminology out there, but these are the basics. So this is called policy. But before I go into the mathematical description of that, let's think about a certain scenario. Suppose you are in a state S0, suppose you are at home and you want to go to a business place to do a business. Suppose that's stated S1. Now you have two options. You have a highway to go, and you have a local way. Local way is shorter, highway is far longer, but going to highway takes you shorter period of time. And if you want to reach to your business as fast as you can, most likely the action from state S0 you will take it to take an highway. However, if I tell you there are two toll booths on that highway which charge 200 and 1200, and you're only going to make a profit of 1000, and in this case reaching as fast as you can might not be that important, most likely then you are planning to take a local route to get some profit. And if there is a shortcut in between that highway and the local route, most likely you will take an action passing from first toll booth and taking the shortcut and going to state S1, rest of the state S1 from the local route. And if you have a final state of S0, which higher amount of reward, you might take different actions, which we don't know what action we exactly take because we don't know the states here. So bottom line here is this: your action are based on maximum total reward you get, and that's your policy, or in this case optimal policy. You will take an action which will maximize your rewards for each state, and it can be defined with this mathematical equation. So for each state S, you want to use a maximum Q value for that states. And in general, policy can be defined with the following equation, which is for each state, this is the probability distribution of all the action we can take. So after talking all these different terms, let's have some entertainment, what we can do with reinforcement learning. So many of you might have played a game of Pong, and if you're not, it's an old Atari game where on computers where you have your computer, and this is where you play, you are as a player, and this disc will move from one side to another, and your goal is to move this disc past your opponent. So let's say we want to train our AI to play the game of Pong. So let's see what happened when AI is not trained. This is your AI here, by the way. As you can see, AI has no clue what to do, and most likely it will lose the game. And it lost. Now we trained our AI using an algorithm called DQ network, which came out in 2015 from DeepMind. I have adjusted some hyperparameters to train it faster, just because game of Pong is a little easier to train. And if you look at the performance of AI with time, you can see initially it was getting minus 20 rewards, but slowly starts picking up, and further down you are in the path after 1.2 million steps. You're pretty close to the positive reward of close to 19 and 20. So let's see how our trained AI plays the game of Pong. Looks like it's going pretty good here. And it looks like our AI won the game. So now let's move to another problem of half-cheetah. What is half-cheetah? Half-cheetah looks something like this. It's a two-dimensional object. That's why it's called half-cheetah. Instead of 4 legs, it has 2 legs. And remember, when we are playing Pong, the action were discrete, go up and go down. But in this case, the action will be continuous because cheetah needs to learn how to run. And before that, it needs to learn how to walk or stand properly. So these joints can move up and down in a continuous manner. So that's why now you have a continuous action space. So let's see how cheetah is doing when it's not trained. And you can see it doesn't even know how to stand properly. Forget about walking and running. Okay, now let's train our cheetah. This time the algorithm I am using is called augmented random search, which just came out in March 2018, only 1.5 years back. And that's the performance you see. And looks like after 300 episode of playing, our cheetah is pretty good in walking and running based on the rewards I see there, plus 800. But let's see how he's actually doing. So here our half cheetah, and if you see, he's doing pretty good. He knows how to stand and walk, and he's trying to run now. That's not bad after only training for like a couple of hours. Now let's make our problem a little more complex, and here comes the ant. So our ant looks something like this. Now previously the cheetah was only a 2-dimensional problem, but in this case the ant is a 3-dimensional problem, and it has much more joints here. So let's see how is our ant doing before training. And as you can see, it doesn't even know how to stand. Forget about the ant to walk and run. And it has to follow a track, if you see the track over here. Okay, so let's train our ant. This time the algorithm I am using is called Twin Delete Deep Deterministic Policy Gradients, or TD3 for short. It just came out in last year in October. So here's the performance graph for the ant here. Again, it started with a negative, almost negative minus 500, and it's slowly picking it up, and it went up to 2500 reward points. And let's see what actually this means. And if you can see here now that our ant is pretty good in walking now. It's not following the track itself, but it will learn after more training to follow the track also. And this brings us to our last, the restless humanoid. So this is our humanoid. Now you see the problem is more complex. Continuous action space, 3-dimensional, and much more joints here. You see so many joints over here. And due to that, if you look our humanoid before training, it doesn't even know how to walk or even stand. It's trying to do that, but if you can see, because the number of joints are so many, it has no clue what to do. So let's train our humanoid. Same algorithm I use this time, TD3. You see its graph is not that pretty as before. It's going up and down, but it's still making good progress after 10 million steps. So let's see how it actually looks like. And you see it's able to walk. It's not a preferred way of walking if you are a human, but still after a day of training, it's not that for a human to learn how to even walk up a street. And this ends my presentations. There are some resources you can use to learn reinforcement learning. This book is, I found, is pretty good to learn the basics, and these courses are pretty good too. And thank you for your time.